People like to say time is what a clock measures. That sounds respectable. It sounds scientific, and it doesn't explain a damn thing. If I hand you two clocks and ask what time is, pointing to the clocks is just changing the subject. That's like saying a tiger is what a tiger detector detects. You haven't learned anything about the tiger. You've learned something about the detector. Now, there's a very popular story about time. It goes like this. Time flows, it moves forward. The past is gone, the future doesn't exist yet, and the present is a thin little slice sliding along. Everyone nods. But if you stop and ask a simple question, how fast does time flow, the whole thing collapses. 1 second per second. That's not an explanation. That's a joke wearing a lab coat. What Feynman noticed, and what makes people uncomfortable, is that physics never actually uses that flowing picture. Not once. When we calculate anything real, a falling ball, an electron moving through a wire, a planet going around the sun, time just sits there like a coordinate on a graph. It doesn't move. It doesn't flow. It's just another label we attach to events so we can keep track of them. Take something simple. You throw a ball straight up. It goes up, it slows down, it stops, it comes back down. We draw a graph, height on one axis, time on the other. Beautiful, predictive, works every time. But notice something strange. The equations don't care which way you read time. Run the movie backward and the math is perfectly happy. The ball falls up, speeds up, and lands in your hand. The equations shrug and say, sure, that's allowed. So where did the arrow of time go? You feel it. You remember yesterday, not tomorrow. You can unbreak a glass only in cartoons. But the laws we trust, the ones that actually work, don't seem to notice. Here's another example. Imagine two identical clocks. One stays on Earth. The other gets on a fast spaceship, zooms around and comes back. When you compare them, they don't agree. One has ticked less. That's not philosophy. That's experiment. Time itself has changed depending on the path the clock took through the world. So now what is time? Is it something flowing everywhere the same, or is it something that depends on motion and gravity and who's asking? You can't have it both ways. Feynman didn't like explanations that hide confusion behind big words. He would say, if you think you understand time because you've heard phrases like space-time or time dilation, you probably don't. Those are labels. They summarize calculations. They don't tell you what's really going on. The disturbing thing is this. Physics can predict with outrageous accuracy how clocks behave, how particles evolve, how the universe expands without ever agreeing on what time actually is. It's like having a perfect map of a city while admitting you don't know what a street really is. And once you see that, once you really feel how successful physics is without a flowing present or a moving now, you're forced into a very uncomfortable question about whether the passage of time is something out there in the world or something happening inside your head, which is where things start to get seriously weird. So people say, the arrow of time comes from entropy. Disorder increases. That's the explanation. And again, it sounds terrific, very respectable. But if you poke it even a little, it starts leaking. What does it mean disorder increases? Take a glass on the table, you knock it off. It shatters. Everyone says, see, entropy increased, time moved forward, fine. But now ask the annoying question, why don't we ever see the reverse? Why don't the shards jump up, reassemble into a glass, and land neatly back on the table? The usual answer is probability. It's overwhelmingly unlikely, and that's true. But notice what just happened. We didn't explain time. We explained statistics. We talked about what's likely to happen when you have a lot of atoms doing a lot of complicated things. Zoom in, really zoom in. Look at the atoms in the glass. Each one follows simple laws. Push, pull, bounce. Those laws don't know or care whether the glass is whole or broken. They work just as well backward as forward. There is nothing in the microscopic rules that says, please prefer tomorrow over yesterday. That's the part people slide past too quickly. Entropy doesn't say things must happen one way. It says some arrangements are vastly more numerous than others. A broken glass can be broken in a trillion ways. An intact glass, only a few. So when atoms jiggle around, they almost always wander into the messy arrangements. But that's not time flowing, that's counting. Here's a simpler example. Imagine a box divided in half. All the gas molecules start on the left side. You remove the divider. Soon the gas fills the whole box. We say entropy increased, time moved forward. But the equations allow every molecule to rush back to the left side. Perfectly legal. It just never happens in practice because the odds are ridiculous. So the arrow of time isn't built into the laws. It's built into our expectations about large numbers. Feynman found this deeply unsatisfying, and rightly so, because probability already assumes a direction. We talk about systems evolving toward more probable states. Evolving. Toward. Those words smuggle time in through the back door. You can't use time to explain time without going in circles. There's another uncomfortable detail. Entropy depends on how much you know. If you know exactly where every atom is, entropy is low. If you don't, it's high. So now time's arrow seems tangled up with ignorance, with what you can measure, with what you remember. That's strange. Time feels like the most objective thing there is. Clocks tick whether you're confused or not. But the explanation we give for why time has a direction leans heavily on what information is accessible. So we're stuck. The fundamental laws don't care about past or future. The arrow seems to come from statistics. Statistics seem to depend on knowledge. And none of this tells you why you remember the past but not the future, or why the present feels like it's happening now. Once you notice that entropy is not a force, not a law, but a bookkeeping tool, you're left staring at a very awkward possibility that the flow of time isn't something the universe is doing, but something we are doing as we interact with it, which opens a door that physicists are very nervous to walk through. Now here's where Feynman would slow down and get very quiet, because this is the point where people usually fool themselves. We say we remember the past, not the future. That feels obvious. You had breakfast. You haven't had dinner yet. End of story. But stop. Don't accept it so fast. Ask the question the way a physicist would. What physically distinguishes a memory of the past from a memory of the future? A memory is not a feeling. It's a physical record. Something in your brain changed. Neurons shifted their connections. Molecules moved. Energy was dissipated. A memory is a physical object, just like a photograph or a scratch on a record. And here's the key point. Every physical record is created by increasing entropy. Always. You cannot make a memory without dumping heat somewhere, without scrambling things a little. That's not psychology. That's thermodynamics. Think of an old tape recorder. You speak. The tape magnetizes in a certain pattern. That pattern is a record of the past. But the act of recording requires energy. The machine warms up. The room warms up. Entropy goes up. You never get a record of the future because there is no physical process that creates a record before the thing happens. That sounds trivial until you realize what it means. The reason you remember the past is not because the past is special. It's because the past is the direction in which records exist. And records exist only in the direction entropy increases. So now time's arrow is tied to memory, not metaphorically, mechanically. Richard Feynman would say this is a perfectly fine explanation as far as it goes, but it doesn't go very far because it just pushes the problem back one step. Why does entropy increase in one direction to begin with? You might say because the universe started in a low entropy state. That's the standard answer. Early universe. Smooth, simple, very special. Fine. But now you've traded one mystery for a bigger one. Why did the universe start that way? Physics doesn't know. Anyone who tells you otherwise is selling comfort, not understanding. What's worse, the laws still don't care. If you took a snapshot of the universe right now, every particle, every field, every motion, the equations would happily run it forward or backward. The universe doesn't label its states as past or future. That label comes from us because we are systems that form records. Here's the uncomfortable punchline of this part. The feeling that time flows, that there is a moving present, might not be a property of time at all. It might be a property of how complicated systems like brains interact with a universe that started out in a very special condition. Time, in that sense, isn't pushing us forward. We're surfing a gradient of entropy, leaving records behind us like footprints in wet cement and mistaking the trail for motion. And if that's true, then the question changes completely. We're no longer asking what time is. We're asking why the universe permits creatures who experience a now at all, which drags us straight into the strangest idea Feynman ever circled but never fully settled. At this point, someone usually says, all right, let's bring in relativity. That'll fix it. And again, that sounds promising until you actually look at what relativity says instead of what people think it says. Relativity doesn't say time is relative in the sense that it's fuzzy or subjective. It says something much more disturbing. There is no universal now. That sentence alone should make you uneasy. Imagine a long train moving very fast. Two lightning bolts strike the front and the back of the train. To someone standing on the ground, the strikes happen at the same time. To someone on the train, they don't. One happens before the other. Who's right? The answer is not both. The answer is neither owns the truth. There is no single fact of the matter about simultaneity. That's not philosophy. That's physics. What that means is that the idea of a present moment shared by the entire universe simply does not exist. There is no cosmic clock ticking everywhere at once. The universe doesn't pause together and say now. So what does exist? Events, just events. A flash here, a collision there, a neuron firing in your head. And they're all laid out in what we call space-time. People draw space-time as a block, past, present, future, all sitting there together. They call it the block universe. Many physicists hate that picture, not because it's wrong, but because it offends our instincts. If the future already exists in some sense, what happens to choice, to becoming, to change? Feynman was very careful here. He didn't like metaphysical conclusions dressed up as equations, but he also refused to pretend the equations said something comforting when they didn't. Relativity doesn't say time flows. It doesn't even say time passes. It says events are ordered differently depending on how you move. That's it. The mathematics works beautifully, but nowhere in it is there a moving present sweeping across reality. So where did your feeling of now come from? You can point to your brain. You can say consciousness stitches events together. Fine. But now you've admitted something radical. The most vivid feature of time, the thing that makes it feel real, isn't in the equations at all. Here's a concrete way to see the problem. Imagine a space-time diagram. Your life is a line through it, from birth to death. Every moment you'll ever experience is a point on that line. The physics doesn't highlight one point and say, this one is special, that one is now. All points are treated equally, yet you experience only one at a time. So either physics is missing something essential, or the feeling of temporal flow is something that emerges only when you look from the inside, as a system embedded in the diagram, not from the outside where the equations live. And that's the crack Feynman kept worrying at. If time doesn't flow in the fundamental description, but it feels like it flows in experience, then the problem of time is not just a problem about clocks or atoms. It's a problem about perspective. And once you accept that, the next question becomes unavoidable. Is the flow of time something real that physics hasn't captured yet? Or is it an illusion so convincing that even physicists keep trying to build it into the laws, which leads straight into quantum mechanics, where time starts misbehaving in an entirely different way? Now, just when you think time is already strange enough, quantum mechanics shows up and says, you haven't seen anything yet. People often say quantum mechanics is weird because particles are waves or because cats are alive and dead. That's all window dressing. The real problem is deeper. Quantum mechanics doesn't know what to do with time either. In classical physics, time is a parameter. You turn the knob, the system evolves. Simple. In quantum mechanics, you still write time on the page, but something funny happens when you ask how change actually occurs. Take the double slit experiment. An electron leaves a source and hits a screen. In between, you don't say it took one path or another. You say it takes all possible paths, every crazy zigzag path you can imagine. And here's the important part. Those paths aren't ordered the way a little object moving through time should be ordered. They're summed all at once in a mathematical expression. That's not poetry, that's calculation. Feynman loved this because it worked. You add up all the possibilities, and out pops the right answer. But notice what's missing. There's no story about what the electron is doing moment by moment in time. The theory gives you correlations between events. Source here, screen there. It does not give you a movie in between. Now consider measurement. You let the electron fly freely. You get an interference pattern. You watch which slit it goes through. The pattern disappears. Something about observing changes what happens. So when did it change? At the moment of measurement? But what moment? According to whose clock? Quantum mechanics lets you calculate probabilities of outcomes at different times, but the act of measurement itself sits outside the smooth flow of the equations. It's like the theory needs time to run, but then steps outside of time to explain how results appear. That bothered Feynman a lot. He didn't like mysteries hidden behind the word measurement. He would say, if you can't explain it with a physical process, you don't understand it. Here's a simpler example. Imagine an unstable atom that might decay. You can calculate the probability it decays in 1 second or 10 seconds or a year. But until it decays, the atom is described as a superposition. Not decayed, both. What does that mean in time? Is it undecided until the last instant, or is that just a bad way of talking? The equations don't say there is a sharp moment when reality makes up its mind. That idea comes from us because we experience sharp moments. Once again, the math works. The predictions are perfect. And once again, the thing that feels most obvious about time, the idea that things happen now and then move on, is not clearly present in the fundamental description. So now we have a pattern. Classical laws don't care about time's direction. Entropy explains the arrow only statistically. Relativity removes a universal present. And quantum mechanics describes change without a clear story of what happens in time at all. At this point, Feynman would lean back and say, maybe we're asking the wrong question. Maybe time is not the stage on which physics happens. Maybe it's something that emerges from the way we connect events. And if that's the case, then the really dangerous thought is this. Perhaps the future isn't becoming real as time passes. Perhaps it's already there in the same sense the past is. And what we call the present is just the slice we're equipped to experience, which leads directly to the most unsettling implication of all, the one that even physicists try very hard not to think about. All right. Now we're standing at the edge of the thing Feynman circled again and again without ever pretending he had nailed it down. Suppose time does not flow, not in the equations, not in space-time. Suppose the universe is just a gigantic collection of events laid out with relationships between them, earlier than, later than, because here affect there, but no moving spotlight called now. Then what in the world is happening when you feel time pass? Here's the dangerous idea. The feeling of passage may not correspond to anything moving in the universe at all. It may correspond to how information is arranged along your particular path through space-time. Think about a simple physical system, a row of dominoes, all standing. You knock the first one, they fall one after another. You say time is passing. But if you freeze the whole thing and look at the entire pattern, all the dominoes are just in different states at different positions. The motion exists only if you watch one piece and compare it to another. Now replace dominoes with brain states. At one point along your world line, your brain contains a record of breakfast. At a later point, it contains a record of lunch. Those records are physical. They're arranged in a particular order. And crucially, each state contains records of earlier states, but not of later ones. So when you move from one brain state to the next, it feels like time flowing. But from the outside, nothing is flowing. There is just a sequence of states, each one containing traces of others. Feynman liked explanations that didn't sneak in extra machinery. This one doesn't add a flowing time. It explains the experience of flow as a structural feature of records. But now comes the part people really don't like. If that's true, then the future doesn't need to be created. It already exists as a set of states that do not yet contain records of one another. You don't experience them because the particular state you are in doesn't have access to those records. That sounds like determinism, and everyone panics. But slow down. Determinism is about prediction. This is about description. Even if the future exists in this block-like sense, you inside the block still cannot know it, because knowing is a physical process that would require records, and those records would themselves have to come from entropy-increasing interactions. In other words, the structure of time prevents you from seeing ahead, even if everything is laid out. This is where Feynman would shrug and say, look, physics doesn't care what makes you comfortable. It cares what you can calculate and what you can test. And all the successful theories are perfectly consistent with a universe where nothing flows. What they are not consistent with is a universe that singles out a universal present. So the great mystery flips around. Instead of asking why the future is open, we ask why the past feels fixed. Instead of asking why time moves forward, we ask why our records are arranged the way they are. And once you ask it that way, you see the real puzzle is not time itself, but the special initial condition of the universe that allowed entropy to rise and records to form at all. Which means the deepest question about time is no longer a question about clocks or equations. It's a question about why there is something like history in the first place, which is exactly where Feynman would stop pretending to understand and start smiling, because that's where honest physics ends and the last part of the story begins. So here we are, at the end. And if you were hoping for a neat answer, a bow on the package, you're going to be disappointed. Feynman would insist on that disappointment, because this is one of those places where pretending to understand is worse than admitting you don't. And what did Feynman really discover about time? Not a new equation, not a hidden variable. He discovered something more unsettling. That time, as we experience it, is not obviously a fundamental ingredient of the universe. The equations don't need it to flow. The laws don't point to a now. The arrow doesn't come from the rules, only from the conditions. And the conditions themselves, the absurdly low entropy beginning of the universe, are unexplained. That's the part nobody can explain. Why was the universe so smooth, so orderly, so special at the start that entropy had somewhere to go? Why wasn't it born scrambled? If it had been, nothing interesting would happen. No stars, no chemistry, no memory, no you asking questions about time. All our explanations of time lean on that fact like a crutch and then quietly look away. And here's the honest conclusion. Time might not be something that exists in addition to the universe. It might be a way certain complicated arrangements inside the universe keep track of one another. A bookkeeping device that feels like motion when you're one of the books. That doesn't make time unreal in the sense that money is unreal. Money is a social construct and still very effective. Time is an experiential construct and still unavoidable. You will age, you will remember, you will anticipate. None of that goes away just because the equations are indifferent. But it does mean something important. The feeling that the present is marching forward might be like the feeling that the sun goes around the earth, natural, immediate, wrong at a deep level. Feynman never claimed the final picture was known. In fact, he liked to say that if you think you understand something completely, you probably don't. The problem of time sits right at the edge of what physics can currently say without lying. We can calculate, we can predict, we can build clocks so accurate they lose less than a second in the age of the universe. And still, when you ask what time really is, the best answer physics can give is a long pause, followed by, we don't know. But that's not a failure. That's a sign you're asking a real question. And maybe the most Feynman-like thing you can take away from all this is not a theory of time, but an attitude. Don't confuse a label for an explanation. Don't accept comfort over clarity. And don't be afraid when the universe refuses to line up with how it feels. Because the fact that time works so well without explaining itself might be telling us that the deepest truths are not the ones that feel obvious, but the ones that still make us uneasy after we've done all the math.